My name's Rowan Hart. I'm a security researcher at Intel. I've been there about a year. I graduated from Purdue in December from the master's program. So I'm pretty fresh, but my focus and the team that I'm on is focused on system software security. So that means basically kernel and below. So we'll talk about that stack, but that's a little bit of my background. I'm very focused on fuzzing, symbolic execution, program analysis, that type of thing. And my main weakness is that I never use any of the tools I make. I just make the tools and then hope somebody will pick them up. First of all, don't sue me, please. And also, more importantly, don't sue the company. And this slide says, as far as I'm aware, you're not allowed to, so we're all good. So there's a full talk about fuzzing, so I'm not going to go super in-depth, but just by show of hands, who knows what fuzzing is? Okay, almost everybody. Excellent. That's kind of what I figured. And who has used AFL++ in the last 2 years? Okay, pretty good, pretty good. So OG fuzzing, cat dev urandom into your binary, shocking amount of stuff crashes. This was, I was a teaching assistant in school, and this is actually one of my hidden test cases on every assignment was this. Not many points, but not a whole lot of points gotten on that one. So nowadays, we do it a lot smarter. We use mutators, we use feedback, we observe the program state, we do symbolic tracing of paths as we're executing, we use hypervisors, all of this stuff. And I'm going to talk about how we've done a little bit of smarter fuzzing. But one thing that I really want to focus on is how fuzzing can be used not just for finding O-days in stuff. You know, that's a great use case for it. Gets you a lot of clout on Twitter, or X, whatever it is. But you know, we can use fuzzing for a lot of more normal development practices as well. Differential fuzz testing allows us to, if we're developing a new version of a product, test against the old version of the product and make sure that things function the same so users won't see discrepancies in how endpoints are behaving, that sort of thing. We can use it for property testing and say, okay, instead of building a unit test with 50 cases, we're just going to say this is never allowed to be more than 5, fuzz it, make sure it's never more than 5 after 10 minutes, and you're pretty much good to go. So things like that are really good applications of fuzzing that we want to see adopted more as we do what my team is focused on and shift fuzzing, as we say, to the left, which is make developers do it instead of having a red team come behind and clean everybody up, because it just doesn't scale when you're trying to have a team of 8 people fuzz 100 projects a year. It's just on a numbers game, it doesn't work. So fuzzing's super effective, but not a silver bullet, of course. We still need those red teams to come behind, and we want them to focus on things like, if you were watching last week, the libwebp bug, where fuzzing probably isn't going to find that one. As a summary, basically, you had to have 6 trees, data trees, constructed exactly correctly, and then you had to mess up the last one so that it would be corrupted. The fuzzer is going to have some trouble reaching that state. It might get there eventually, 1,000 years, 2,000 years, something like that, but we need manual analysis as well. So that's a very important thing to keep in mind building fuzzers. So at Intel, we use a lot of fuzzers because we have a lot of software. As you probably are aware, we make CPUs, but we also make everything above that in the tech stack. We do CPUs, we do the firmware that runs on them, we do the microcode below that firmware, we do the operating system on top of it, we build the driver support for all of the hardware that we produce, we build user space applications for the operating system that we're helping to support, and we build web applications that you can reach over the internet running on those operating systems and user space applications. So we need fuzzers for every layer of that stack because we want to test for those types of assumptions that we covered, as well as, most importantly, for security vulnerabilities. So this is not an exhaustive list, but this is just kind of an overview of some examples of fuzzers that we use for various levels of stuff. We have the developer of BooFuzz here. Go talk to him at some point. Great for network fuzzing. There's a workshop later. And then we also use Wrestler for REST APIs and web API fuzzing. Obviously, user space is one of the most fuzzed spaces. And we have really good support for enabling developers to do user space fuzzing with libfuzzer. You add a compile flag, you write 4 lines of C, and you're basically done. You can't really ask for much better than that. And that's the kind of development practice we want to bring down the stack, because as you go down, it gets more difficult to harness things and more difficult to fuzz them. So In the kernel, we move towards hypervisor-based fuzzers because you need to boot a machine over and over, you need to run it in specific device test paths. So for example, you need to fuzz virtual I/O drivers, you need to boot your devices, and you need a hypervisor for that. Of course, most hypervisors are based on QEMU. So from our most recent server CPU release, the Sapphire Rapid CPUs released around January to March, and QEMU support was added in April. So that's pretty good. That's really fast on the QEMU developers, and they're amazing. But we need a little bit better than that if we want to test our firmware before the CPUs come out. So KFL, KFX, those are hypervisor-based fuzzers. They both require QEMU support because they're using it under the hood. Below that, when we're looking at system management interfaces, we have an old tool called Excite, which I'll talk about. This project is actually a successor to that one. And then even below that, for some very custom deep features, like the Intel management engine, teams are generally using custom forks of fuzzers, fuzzing things that are built in very specific ways. So we get pretty hardcore there. And then even below that, when we're at the hardware description language layer, where we're looking at VHDL models of CPUs that are not produced, not even modeled, not emulated, nothing, we can fuzz them at the RTL or VHDL layer with tools like PreciFuzz, which I think is actually on GitHub now, so you can look that one up as well. So moral of the story, there are a lot of fuzzers. So let's rewind, and let's look at the use case that my team is trying to tackle. So we have CPUs, we want to make the CPUs, and we need to ship them with firmware when we ship the CPU. And developing firmware takes a long time, almost as long as designing the actual chip itself. So you have to do the firmware design while you are doing the chip design. The problem with that is, how do you run firmware for a chip that you don't have? You need to virtualize, emulate, etc. But the use case most of you may have seen is noticing something sketchy going on with your router. And I was in this situation a while ago. I was looking at my router's JavaScript, which you should never do, tonight, and noticing some very interesting things that CenturyLink had put in there. So what I did was I hit firmware update, got into Wireshark, grabbed the firmware download. It basically just gives you an entire root file system, so you unpack that. And then it actually downloaded an old version because it has a bug. So you need to fix the vendor's code now, and you need to download the real version. Yes, fun fact, my router updates itself to the same version it's on only. So you need to download the real version by guessing their URL scheme. Then you run QEMU in the unpacked root file system. And if you're really lucky and your router is an x86 machine, it'll probably run. But more likely, it's running MIPS, so you're going to need to Google that. And somebody's blog is going to tell you that libnvram.so from this GitHub repo that you need to hit translate on is going to work. So you download it. And you compile it on your machine. You don't read the code. And then you put it in the root file system, and it indeed does work, because some people are really smart. So you run QEMU. Fun fact, this is actually by far my favorite way to emulate routers, is just run QEMU user on BusyBox in the unpacked root file system. That's all you need to do. You don't need to do QEMU system. You don't need to do devices in most cases. Just do QEMU user with the unpacked file system. And then, yeah, if you do need to do devices, good luck. So for us, it looks a little bit different at Intel. We're not working on your Zixel router in your wall that's been there for 15 years. We're working on new stuff, and we don't have the chips for it. We don't have QEMU support. So we have a few options, basically, for how we want to run the firmware that we want to fuzz. We can run it on real hardware. We need the hardware, so that one's out. We can virtualize the hardware. Totally doable and will be done, but usually it takes a long time, which is kind of the issue, and is not done early in the chip development process. Or we can stub out the hardware. So this means you go through your firmware C code, anywhere where it makes a call down to some feature in hardware, you just replace it with the C function that returns the right value. So, if you're reading a model-specific register in your CPU, it's probably not going to work if you don't have it, but if you just replace that function with something that returns 0 every time, you're probably going to be okay. So, we don't have the CPUs. We don't have virtualization. And most importantly, we do not have any time. So it's a really hard sell, as many of you are probably aware, to go to a development team that has a bunch of sprints and a bunch of upcoming deadlines and say, hey, we need you to stub out all of your hardware functionality so that we can fuzz your stuff. It's just not going to happen. So developers don't have time, QA doesn't have time, validation doesn't have time, and the red team has some time, but there's only 5 of them. So what we need to do is make it possible for developers to fuzz stuff without doing any work. So they need to be able to install it. And they need to be able to copy and paste all of the instructions to install it. Because, again, and this is not a knock on any developers, it's our fault as fuzzer authors for making our install processes so difficult. If you have more than 5 options, it's too many. So you need to be able to install with a couple steps. You need to be able to add your fuzzer into whatever development process is already happening. So if your development team is using makefile-driven development on Linux, and it's just pure bespoke makefiles, you need to work with that. If they're using Visual Studio and they have a bunch of solutions everywhere and they're using all of Microsoft macro systems and whatever they do, I'm not a Windows person, you need to work with that as well. And finally, it needs to be a good fuzzer. So despite all of the ease of use things that we need, which are, in my opinion, the most important, you can't just pipe dev urandom into your program because that's not going to cut it. It's 2023. So we made that fuzzer in theory. It's called Target Software Fuzzer for SIMICS, which is a very nice legal approved name and not the original name we picked. But luckily, it kind of sounds like TSFFS if you say it badly enough, so I drew some art for that, and away we go. So TSFFS is based on a simulation platform that we use at Intel that's also publicly available, which is why I'm here telling you about it. It's called Simix, which, as far as I'm aware, doesn't actually stand for anything, kind of like QEMU doesn't stand for anything, except used to stand for Quick Emulator. And what Simix is a full system, cycle-accurate device modeling software. So that device can be, and usually is, a CPU, but it can also be a graphics card, a network interface, it can be a TPM. Any of these things are modelable in Simix. And basically what you do, you download Simix, you create a project, you add a bunch of existing models to it, because they are tough to make, not as hard as actually designing the CPU, but as you can imagine, modeling a modern CPU is quite difficult if you've ever tried to write an emulator. So you plug in your server CPU, you plug in a TPM, you plug in a ARC graphics card or whatever it may be. You don't get those models. And then you boot it, and it runs. Cycle accurate, simulated, including power, thermals, all of that simulation on your Linux system in user space, which is the key. So TSFFS is, of course, very AFL++ style. It's feedback directed. We have comparison logging with Red Queen. It's snapshot based, which is free for us because we're using Simix, which has snapshots. You can launch as many processes as you want, and they all synchronize together. So we'll get into some Simix specific stuff in a minute, but that's very useful for our specific use case. And yeah, basically, we threw the kitchen sink of all current system software fuzzing research into it. It has MOP, it has auto tokenization, it has all kinds of mutations. There's a short list of things it doesn't have that we'll get to at the end. So why Simix? First of all, the #1 reason is because everybody at Intel is using it for all of their firmware development, which means if everybody's already using it, we can just ask them to plug one thing into this, and now it'll fuzz instead of just running your software. Not bad for the developer perspective. From the fuzzer design perspective, it's pretty amazing to work with, having come from a let's fork QEMU again background. Because instead of adding functionality to QEMU to add snapshots or add introspection, which, fun fact, is still not allowed in QEMU because of GPL violation rules, unless you have a fork, which there are several. If you want to read a register, you call a function. If you want to read memory, you call a function. If you want to figure out what the thermal change over the execution of your new hardware instruction was, you call a function. If you want to get the hash of all of your model-specific registers for the CPU that you're running, you call a function. So there's a lot of really powerful stuff, and we're only kind of scratching the surface at the moment, but a lot of really powerful stuff you can do with Simix that kind of is enabled because it's not designed as a scalable, cloud hyperscaler, let's give people virtual machines emulator. It's designed as a test bed. It's designed for debugging and all of that stuff. So second key feature is that I had to do about 1 hour of work to get snapshots working with my fuzzer. Because once again, if you want to take a snapshot, you call a function. And then if you want to restore to it, you call another one. So Simix basically provides all of the hard stuff for us to build on top of and build our fuzzing research on top of. So that's great for us. We have models for all of our upcoming software, but what about all of you who maybe do not work at Intel? So Simix is publicly available. You can go on Google. If you say download Intel Simix, there's a web page, you can download it. And I actually found this out last week when I was checking to make the slides, but it has all of our currently available CPUs in it. So if you want to go home and run a Sapphire Rapid CPU, you can do that, actually. If you want to do some research on those, have at it. They're available to you. So 12th generation client and Sapphire Rapid server CPUs are available in public Simix. So it's at least on par and slightly ahead of actually QEMU's release schedule for being able to emulate or simulate modern CPU designs. We also have publicly available RISC-V models, which the fuzzer doesn't support yet, but definitely will, because there's a lot of people who are very interested in doing RISC-V research, fuzzing firmware for RISC-V platforms like all of the Pine and Orange Pi type boards and things like that, as well as mobile phone devices. And finally, for developer experience, we get free time travel debugging, bug triage, read all of the registers, read all of the memory, forward and backward step, inspect everything, and figure out why your firmware is crashing, which is really important for the developers. When they're categorizing their bugs and figuring out, okay, what stuff do we work on first? And B is very useful from once they start to work on it, it's very quick to get to the root cause of the issue when you have basically every possible piece of data available to you. Second thing we do to get some free stuff is we don't fork AFL. So this is not a talk about not forking AFL, but I've done it 3 times. I'm sure some of you in the audience have done it probably more than that. But there's a better way now, and it's called LibAFL. So LibAFL is a library that's written in Rust, and essentially what it does is implement every part of AFL++ as a library that you can just import from, create your own fuzzer using all of those components, which includes basically from the binary up, you have a backend, which may be QEMU, it may be Nix QEMU, it may be KVM QEMU, whatever it may be. We have Frida, which if you're an iOS or an Android reverse engineer or security researcher, you probably know Frida and are a big fan. And Tiny instrumentation for really good Windows speed and instrumentation. And then, of course, you can run native binaries, you can run forking binaries, you can run, harness your library, whatever you may want to do with it. And the modular approach is super helpful because you kind of pick a backend, you pick all of your fuzzer capabilities. So if you need concolic tracing, LibAFL has it. You can add that in. Not every target needs it, so you get to choose whether you want to enable various stages. You want to enable Red Queen. Your program is parsing text, so you want to enable Grimoire, which is a grammar mutator for mostly English text. All of those are options with LibAFL. So if you are a researcher in fuzzing and you're trying to implement new techniques, for example, you have a new power schedule, you have a new mutator, LibAFL is kind of the perfect place to do that because you just write it, you test it out locally, and then when you're done, you can upstream it, and then everybody else can use it. You can go to the conference and talk about it, but it'll actually probably get used in production if you upstream it to LibAFL. Instead of, like me, your 3 or 4 AFL forks sitting on your GitHub for years with 16 to 25 stars, pretty respectable, but not a whole lot of active use in industry or research. So, big shout out to the LibAFL team for putting together such a great tool. And I actually did license this meme from the original creator, so you can't sue me for that either. All right, so that's what we get for free. So this is what we are giving other people for free. As I mentioned, pretty much everybody working on firmware and BIOS at Intel uses Simix every day. They, make some changes to the BIOS, they boot it in Simix, they see how it works, make some test cases for it, iterative development process. What we've given them is a 3-step install process, which is not 1, but is a little bit less than the 5, which I use as my guideline. So not bad. You install Rust, you set an environment variable, and then you run build. Not great. We can reduce it to 2, technically. Maybe next week when we merge some patches. Then to enable fuzzing in an existing Simix project, you add 2 or 3 lines of code. You basically initialize the fuzzer, and then you say, here's the things that I want to consider as crashes, and then you say, go, fuzz it. You also have to add a harness to your C program, unfortunately. We have a triage mode where you drop directly into the Simic command line interface, which gives you all of the classic debugging features. You can kind of think of it as super GDB. And then anything that gets merged in Simix or LibAFL, we get immediately. We pull in new LibAFL stuff. Somebody fixed the low-level message passing to be a little bit faster. So now when you run a parallel instance, you get almost double the executions per second. And we just continue to get improvements like that for free from the community, which is great, because there's only a couple of us working on this. So the way the fuzzer works, there's a launcher, and this is all essentially LibAFL concept. So LibAFL provides this launcher, and you say, give me 64 cores of fuzzers. And it says, okay, starting 64 fuzzers. Each of those 64 fuzzers starts up a front end, which is the LibAFL side, and this is doing your analysis of your coverage, analysis of your comparison logging. It's generating mutations of your test cases. It's managing the synchronization of your corpus, all of that jazz. And then the LibAFL side talks to the Simic side, and Simix actually is a library as well, which we have bindings for in Rust, and we basically just program against Simix as a library. So that's why it's easy to use, is because it's not a binary. And we just load up a module, also written in Rust. Fun fact, none of Simix is written in Rust, and it doesn't support Rust. So they were a bit confused when I told them what I'd done. So we load up a Simix module in Simix. That module handles basically catching events. So when specific instructions happen, comparisons and such, it logs those and adds them to the coverage map. The Simix side also handles snapshots of save and restore. So we'll look at harnesses in a second. And then, yes, okay, that's all it does. All right, so I'm not brave enough for a live demo. I have some GIFs for you. Oh, and that's really small. I'm so sorry. Okay, so I'll just talk through it. So we've got a directory here. We have 2 files in the directory. This is what you get when you go to the website and you download Simix. You get a Intel Simix package manager tarball, and you get a .ispm file, which is a basically just an archive of all of the packages that are publicly distributed. So to install, we create a directory, very magical, and then extract the Intel Simix package manager. And yeah, so the package manager essentially just manages Simix projects and allows you to install packages. In the public release, there's only one way to install the packages. It's from the bundle, but internally we have a bunch of ways to do it, so it handles those. And that's just a Node app, so pretty easy to unpack and run on most platforms. So then we go ahead and install your package bundle. This is, by the way, not technically included in those 3 steps because internally developers have already done this. So anybody who's counting, you need to start over. So included in the public Simix distribution is Simix Base, which is the simulator and all of the stuff in it, the x86 Quick Start platform, and the and the Quick Start CPU platform, which basically that's what provides all of our CPU models. So all of the, Sapphire Rapids and such. That's where that is. It has RISC-V CPU, and it has some training and stuff. And then there's one here called DOSI Base. I think that's how you pronounce it. And that's the one that gives you all of the thermal and power trace stuff. So if you're interested in side channel stuff, that's where you want to look. No, you can't sue me for that one either. Yeah, so once you've installed Simix, pretty painless process. You go ahead and clone our repository. This is where the 3 steps starts. And we'll get to the fuzzing, I promise. So you clone a repo, cd into it, set an environment variable through the cool kid modern way in a .env file, pointing to the place that you just unpacked all of your Simix packages. And the reason we have to do that is because I made a mistake early in the design of this, and this will be fixed in about 6 days. So, and then we just build, and we pass a feature to tell the cargo build system, if you haven't used it, is pretty wonderful. It just builds Rust, and it's quite fast and quite ergonomic. So this is one of the other advantages of using LibAFL, is it lets you justify building everything in your project in Rust, which makes you much happier. All right, so we've got a fuzzer now. Go ahead and run it with some help messaging, which in our cases is actually quite long and complete, because that needed to be done before open sourcing. So now that you have a fuzzer built, we can go ahead and take a look at how do we harness a project for fuzzing. So we have one example. It's called it's the mini example in our repository, and basically this is the smallest possible UEFI app that you can do. So we use Ninja to build it, and we'll see in our Ninja file we're including an include file here, and that's what we're going to take a look at first. So there's 2 steps to harnessing. You include a file, and then you add 2 macros. So this is the file we include. And essentially what this gives us is a macro that says start and a macro that says stop. So during normal execution, the application will run. We'll get to the start point. It says, here's a buffer, and here's how big it is. And the fuzzer says, cool, I'll fill that with stuff. And again, way too small for anybody to see. But we've got start, stop, stop extended. Don't worry about stop extended. Harness start, you pass a buffer, you pass a size. The fuzzer fills the buffer up, and then it writes back the actual size of the data it wrote, because we don't want to smash the stack via the fuzzer. We want to smash the stack via the fuzzer, if that makes sense. All right. So after that, we just need to add a couple lines to our C file, and then we're good to go. We can build it, and we can start fuzzing this EFI application. So up at the top, we just include a header. It says include tsffs.h. And then if you're a normal person and you haven't read the UEFI spec, you can probably just ignore all of those tables. If you have read the UEFI spec, you'll recognize those. Basically, I've just defined the minimum number of tables I need to print stuff. And tables in UEFI are just resources that are provided by the hardware via standard interface. You can call functions on them, you can pass data to them, and they will do things such as write it to the screen, move the cursor, take some input, etc. So we have a password checker, probably pretty similar to what you would see in the CTF that I think is going on today. Kind of a 101 CTF example here. If we put in the password fuzzing, it'll crash, which is great. This is actually very hard for fuzzers built before about 5 years ago because there's a lot of magic value checks involved in this. It's really easy now because we have modern fuzzing techniques, so a little bit of evolution for you. So down here at the bottom, we're declaring a buffer, we're declaring a size, and then we are calling our harness macro with the buffer and the size. Really riveting stuff. But it's good that it's boring because this is what the developers have to do. They have to include something and they have to write 5 or 6 lines of code. Minimal example. In real life, usually you read some stuff from the fuzzer, you write it to disk, something else reads it from disk. So you have to do a little bit more work. But in general, it's been a pretty easy process for most of the teams internally that we've worked with. So we're quite happy about that. So now we've built our harnessed EFI application. And finally, we can go ahead and update our script with the 3 lines I mentioned earlier. So we have, let's see, what am I doing? Okay. So there's a scripting language for Simix. It's Simic Scripting. It also supports Python scripting. Simic Scripting I actually find, even though I was a Python developer in a past life, to be a lot more ergonomic for this particular use case. So basically what we do is all this is doing is after boot, it's booting to a hard disk, and then it is putting in up, escape, enter to click the UEFI shell in the BIOS. So it's entering things on a keyboard and then waiting half a second. So nothing very technologically advanced. Down here at the bottom is where the advanced stuff happens for fuzzing. So the first thing we do is we download our EFI to the file system. And we just do that using a built-in Simix utility for downloading stuff onto file systems, which is quite nice. So we type in download mini.efi, and then we wait half a second, because if you don't do that, you end up with a lot of stuff over top of each other. And then we stop our simulation. So we've downloaded our EFI, and we are no longer simulating. After that is when the actual configuration of the fuzzer happens. So we can access this because it's been loaded for us by the fuzzer. Basically, we just have a property, and if you were interested in checking this out, basically the @ sign at the beginning of lines in a Simic script means it's Python. So you might as well be writing Python here. And indeed, it does get past the eval. So what we do, we say init, that says, OK, module, go ahead and start up. Start your logger, connect to the fuzzer front end, et cetera. Then we add a processor. So right now, this is a single-threaded fuzzer. It supports multiple threads, but we haven't tested it. So I'm making no claims there. We add a processor, which is just our only CPU core that we're running. And this is an x86 model. And then we say add fault 14. That means if a page fault happens, the page fault will be considered as a crash. So because this is UEFI, we don't have virtual memory set up or anything. Page fault means we wrote or read out of bounds. And after that, we just input the name of our EFI application followed by a new line, and we're good to go. So it'll start running our UEFI application, and the fuzzer takes it from there. So let's take a look. It felt like I was typing really fast when I recorded this last night. So we pass a bunch of options to the fuzzer. So we pass a project, which is a Simix project, and a Simix project is basically just a directory that you get that has certain models in it. So this one will have x86, obviously, because that's what we're fuzzing. We pass an input corpus. We pass a directory to put any solutions we find, which is code for crashes. We set our log level. We say 1 core, because if we throw 64 cores at this little poor test program, it'll get overwhelmed quite quickly. And then we pass the executable that we're loading, and that's actually used for auto tokenization. So we parse the PE executable, we extract all of the strings from it, and use those for very, very efficient mutations against string checks. And then right now, we have a bunch of arguments called -- file, which copies a file into your project. And then, if I could type a little faster, at the very end, we run the script that we just created. So that script we were looking at that has the initialize fuzzer, page fault is bad, and then we start it up. So you see a bunch of logs from the simulation, and then you start seeing a bunch of logs from the fuzzer. And you probably can't see, but this is just LibAFL's default logger format. We get our runtime, we get the number of clients connected, we get the size of our corpus, we get the number of objectives we've found, we get the amount of coverage that we have in edges, and where is it? Right here. We got an exception with page fault, which means our fuzzer has very quickly passed all of our string checks, and we get a page fault. So great, we have a crash. Developer says, cool, I'll put that in Jira. And we say, no, you need to figure out why. So to figure out why, we add one flag, which is -- repro with the input that caused the crash. And this will run just the same as before, except now it drops into the Simic Shell. So from the Simic Shell, we can do whatever we want. So we can disassemble the current instruction. We can forget how to type Simix commands. There we go. We can view RAX as non-hex, which is completely useless. Oops. All right, well, we're gonna miss the rest of that one because I don't know how to replay the GIF. Oh, it's actually still going. Okay, we can print all of our registers out, and then pretty much the best feature of triaging in Simix is bookmarks. So we can just reverse to the start of this test case where we started executing right after the test case was written into memory. So we reverse there, and then we can just single step through the entire execution under that test case to see what happened, where did this go wrong. So sometimes the point where the program crashes is not really the point that you care about when you're debugging the crash. So being able to step through the entire process is super nice. And at the end, we can continue and we get the crash again. So, all right. That's the whole feature set. There's a couple things I didn't mention, like you can set a breakpoint, which in Simix is more like a watch point in GDB. You can set read or write on some memory, and if it's read or written, that's bad. And then you can also set executable watch points where if certain code is executed, that's bad. And then here's our future roadmap. So these are all filed as issues on our GitHub. If you have ideas, you're more than welcome to file more, and I will take a look at them, or I will ask you to implement them. But yeah, so we want to do some concolic execution. We want to do taint tracking. We want sanitizers, which is the big one, but that's probably an us problem. And yeah, so questions?
All right, if you want to ask a question, come on up to the front so he can hear you. I asked YouTube, and they haven't had any yet as well. All right.
I knew. Is this useful for anybody? Excellent. All right, that's all I need to know. if you have ideas for improvements or fixes that you'd like to see, you can email me. But knowing that at least somebody's interested in it is quite useful. Obviously, it's super useful for us. But one of the reasons I took the job I have now is so that I could publish and open source the research that I was doing. So. Being able to respond to community feedback and make sure it's useful for people outside of Intel is one of. Looking at it. I haven't checked the download stats. We have some stars. We have a couple people have pinged me saying that they tried the examples. At least, okay, so we have at least 4.
Having worked at Intel previously and done something similar to this when Intel was not interested in publishing anything anywhere outside, this is awesome. So thank you for presenting this.
Great, yeah, happy to hear it. That's actually a great question. The first crash I found with this fuzzer was in Simix because I was sending a lot of inputs to a device that was not expecting them. So actually, one of the useful things about this has been, the models are not perfect. And if they are perfect, sometimes they will still crash because the hardware would crash in such a scenario. So you kind of get double dip when you do this fuzzer. You send a bunch of stuff to a modeled device, the firmware might crash, the model might crash. You look at the model crash and you say, wait a minute, this is modeled correctly. That's a problem. That hasn't happened yet, but I hope it does at some point.
Got one from YouTube. Are executable watch points a feature of Simix?
Yes. So basically, the way it works, unfortunately, I should have shown it in the demo. There's no reason not to. But basically, the way it works is you say break some address and then either -x, -r, or -w. And that means you can combine and mix and match those as you want, but you can breakpoint anything. So one obvious use case for that is code and system management shouldn't be running when the kernel or user space is running. So if people are trying to ROP into the management engine, that's probably something you want to know about. So being able to detect things like that with just, and I guess probably the YouTube comment may want to know, it's also applicable over a range, so you don't have to set it for every address. You can say, this whole range of memory, you can't execute it, and if you do, then we found a crash.
For crash deduplication, are you relying on LibAFL, or are you doing some other stuff too with the extra information you have?
I haven't found enough crashes to deduplicate them yet. I've been adding features as they've been demanded of me, so that one is TBD. But likely I would rely on LibAFL for that. They have some stuff you can use stack hashing and so forth. Well, if anybody has any more questions or thinks of anything, you're welcome to message me on my non-listed contact information. I think my Mastodon is on the BSides page, so you're welcome to message me on there. That's probably a good way to get in touch. Or you can just find me around, and I'm happy to chat about it.
All right. Thanks, Rowan.